So, welcome to part four of our electrophilic addition to alkenes discussion. Part four, we're going to move into a different mechanism away from the carbocations and more into the ring formation process. And there's two possible processes that could occur. One when we have a halogen, the other is with this mercury. And I'm going to discuss both of those mechanisms. The mercury one, we're going to kind of go more detail later. I'm just going to show you the addition of the mercury. But when we talk about general reactions, then we're going to discuss, you know, the additional steps of that. But to start, when we have something like this, a double bond, and we add X2, like for example, a halogen, chlorine or bromine, the first step of the mechanism is very kind of complex. We still have our nucleophile and our electrophile, so the nucleophile adds the electrophile. But during this process, we're kicking out X, but we're also having this X form a bond back to the double bond. And so what we're going to get out of this is we break this double bond to form a sigma bond. So we get something like this to X, but X is forming a bond back to the carbon that was in the double bond. So we get something like that. We are losing electrons over here because X is leaving as X minus. So that means this X is going to be positively charged. Notice that the positive charge is not on a carbon. It's not a carbocation. So no rearrangement will happen here. You do not have to worry about the possibility of rearrangement. The next step of the mechanism is going to be X adding to that three-membered ring because it's not that stable, it's very strained. It's going to add to the more substituted side. Because I'm adding X and X is already present, it really doesn't matter that I'm adding it to the more substituted side because regardless you get the same product of which side you add to. Where it's more relevant is when we talk about halohydrins. We'll talk about those in a future video, but if X was something different, you have to pay close attention to the fact that it's actually adding to the more substituted side. And so when we add to that carbon, we need to break that bond here. And in that process, what we're getting is, again, if I were to number these, let's say 1, 2, 3, we're adding the X minus to carbon 2. Let me put it straight up and down here. And then carbon 2 is losing its bond to the X that was in the ring, but carbon 3 is still going to be attached to X. So we would get something like this. So whenever you add X2 to a double bond, each of those X's would add one to each side of the double bond. Now, mercury is the same way. When you add mercury, in this case mercury acetate, I'm going to draw it like this so we can see there's actually two of these acetates on there. Mercury has a lone pair. We're going to add to the mercury. The mercury is going to add back. We're going to kick out one of those acetates. And what we're left with is Hg, one of the acetates, and a positive charge. Now, this doesn't really mean much to us right now. But when we talk about the oxymercuration demercuration reaction, where we do a Markov-Nikov addition of water without rearrangement, that's where this mechanism is going to play more of a role. But just keep in mind that what's happening here is we're forming a ring. There's no carbocation, so no rearrangement can occur. When you form a ring like this, the next thing you add will add to the more substituted side. So if I added X next, it's going to add here, and I would get X and my mercury acetate. So that is the ring formation process for the addition to a double bond mechanism. The next video I'm going to do is going to move into what is known as syn or anti-addition. After that, we'll look at specific examples of addition reactions.